Okay, so with rate of change, it doesn't always have to include height or how fast the surface area or volume is changing. What it can actually refer to is angles as well. So this is more of an uncommon question, but it does come up, so it's important for us to go through. So let's have a look at question 6, which is what we have here. So we have a searchlight on the ground and it detects and tracks a plane which is due east of the searchlight. Now this plane is flying back due west and it's at a constant velocity of 240 kilometers per hour and maintains a very constant height of 900 meters above the ground. So again, I just want you to have a go at drawing this diagram before I show it to you, because I always think drawing the diagram is one of the most difficult parts. Okay, so just have a quick go there. So did you get anything like this? So what you have here is the searchlight, which is due east. This plane is due east of the searchlight. Yes, so remember with that, we have it due east. And now the plane is flying due west, which means it's flying directly backwards towards the searchlight. And we've converted this to 0.9 kilometers because this is in kilometers per hour, and it's just better to have everything in the same form as well. And what we have here is x kilometers, which is how far away that plane is from the searchlight. And this is our theta, so our angle that we'll be working with. Now, what we know is that the plane is flying back towards that searchlight. Can you see that? It's getting closer and closer. So that's why it's actually traveling at the velocity of negative 240 kilometers per hour, because it's going backwards. Okay? So its change in distance is going to be dx on dt equals to negative 240. The other thing that we can use is that because this is a right angled triangle, we know that tan theta will equal opposite 0.9 on adjacent, which is x kilometers. So remember, part of all of this is trying to get as much information as you can from the question. Okay, so part A here wants us to show that dx on d theta equals to 0.9 on negative sine squared theta. So the first thing we can do is use this here, all right? And because it's dx on d theta, we're going to make this x equals 2. So x equals to 0.9 on tan theta. Now, that's the same as writing 0.9 multiplied by tan theta to the power of negative 1. And let's find the derivative of that. And because it's in terms of tan theta here, so that's why you have d theta down the bottom. So this is just a constant. Subtract 1 from that becomes negative 2. And remember, you always have to multiply, because it's a chain rule, by what's inside the bracket. Derivative of that, so derivative of tan theta. Now, this tan theta to the power of negative 2 is just going to become 1 on tan squared theta. It's theta squared. And this over here, what's the derivative of tan theta? Do you guys remember? Yeah, exactly. It'll become sec squared theta. And now remember, tan theta equals to sine theta on cos theta. Yeah, so you have 1 on tan theta, you'll be cos theta on sine theta. And because it's squared, that's why you have cos squared theta on sine squared theta times sec squared theta there. And sec squared theta is the same as 1 on cos squared theta, right? And that's how you can cancel that and that there. So that leaves you with negative 0.9 on sine squared theta. Yeah? So that's how we've shown that this does actually equal to that. So just a little bit of your trigonometry revision over here. All right, let's move on to part B now. So find the rate of change here of the angle of elevation of the plane. So can you see how we're working out the rate of change for an angle now? And of the plane when theta equals to pi on 4 in radians per second. So this in radians here is really important, because you can only work out rate of change when the angle is expressed in radians, not when it's in degrees. Okay, so if you do see it in degrees, you must change it to radians first. And it's also per second as well, so just keep that in mind. Okay, now let's find d theta. Here we found d theta on dt when theta equals to pi on 4. So this is what we need to find. And remember from previously, we've also worked out what dx on d theta equaled to. So we had dx on d theta from the previous question, so just keep that in mind as well. So that one, just from the previous question, we had negative 0.9 and it was on sine squared theta. Just going to write that down the bottom because it's going to come up later. Okay, so firstly, we want to work out what d theta on dt is. We need to change those rates. So we think d theta on something, something on dt. Well, since we already know what dx on dt is, it only makes sense to put dx up here and dx down there as well. So remember how we had dx on dt was negative 240 because it was going backwards. And since we have dx on d theta from part A equals to negative 0.9 on sine squared theta, because that's flipped around, all you need to do, flip it over. So you have negative sine squared theta on 0.9 there, yeah? And then, so we've just multiplied that through, the negative and the negative cancel. And now we know that theta has to be pi on 4, so that we want to work out the rate of change when theta is pi on 4. So all you need to do is substitute it in and work it out in your calculator. And it equals to 400 on 3 radians, remember it's in radians, per hour, because this was all written for kilometers per hour. But do you remember how the question specified per second? So that's when it becomes really important to read the question very specifically. So to change it to per second, we'll divide by 60 to change it to minutes and divide by 60 again to change it into seconds. So that becomes multipliers when you make it on the bottom. And that just gives you 1 on 27 radians per second as the rate of change for that plane to the searchlight. All right, excellent. So just remember that when you work out the rate of change for an angle, it must be in terms of radians. It can never be in terms of degrees.